Hi, greetings from Malaysia, right? A very good afternoon to everybody in Malaysia. And if you're not in Malaysia, perhaps you're in a different time zone. Welcome to the Tech Tarik Time. So this Tech Tarik Time is a program organized by the IEEE Malaysia Communication Society and Vehicular Technology Society joint chapter. Yeah. So with us today, we are very fortunate to have a very wonderful speaker, Prof. Michael Ng from University of Southampton. Hi, Prof. Michael. How are you?
Hello, good afternoon to all of you. So greeting from
Good morning to you.
Hi.
Good morning to you.
Thank you.
Thank you so much for lending us your time for to provide us with the talk today. So before I let you with the topic that you want to talk about, let me just give a brief overview of about Prof. Michael. Prof. Dr. Soon Seng Ng Michael, or well known as Prof. Michael from the University of Southampton, is someone who has been working in the area of quantum error communication. Actually, he has been working in error coding for quite some time. He's an old friend of mine. We've been working under the same supervisor before, right? But he's now one of the founders and officers of the IEEE Quantum Communications and Information Technology Emerging Technical Subcommittee. So without any further ado, I hand over to you, Prof. Michael.
Right. Okay. Thank you, Professor Yusuf, for the introductions. So let me. Okay. Let me go to the full screen. Right. So it's so wonderful to meet you virtually. Although you are in Malaysia, I'm in Southampton, but looks like we are just 60 centimeters away, yeah, from the screen. So my name is Michael Ng. Yeah, I've been known as Michael Ng for many years since I'm in Southampton in 1996 as a student. So I'm now a professor in telecommunications and I'm teaching wireless communications. So just a very brief introduction to you about Southampton. So Southampton is a bit like Johor. It's at the end of at the far south of England, and it is about 120 kilometers southwest of London. The climate here is a bit like Cameron Highland or maybe Genting Highland. Yeah, so it's 2.2 degree in February, 20.6 degree in average. Yeah, on average in August. Population is about 250,000. Population of the student is about 40,000 students, and there are two universities: University of Southampton and also Southampton Solent University. Titanic, yeah, the famous movie Titanic. So Titanic set off from Southampton in April 1912, and the world's first radio news by Marconi was broadcast from Bournemouth to the Isle of Wight. So you can see here, I'm not sure whether you can see my mouse. Hopefully you can. So Bournemouth is somewhere here, and Isle of Wight. Isle of Wight is a bit like Singapore. Yeah, so basically a small island there. And a little bit about the University of Southampton. It's a member of the Russell Group of Research Universities. So a Russell's Group, there are about a dozen of universities, and they receive a lot of funding from the government, especially for the research, research fundings. And University of Southampton is among the top 100 universities in the world. The students, we have about 17,000 undergraduates and 7,000 postgraduates. The School of Electronics and Computer Science was founded in 1946, and it is the biggest and strongest academic unit in the country in electrical and electronics engineering, according to the IET. And we are top in electronic and electrical engineering for many years. So I just checked the Guardian University Guide for this year, and we are still at the top of the league table. So that's good. And there are not many lecturers in the School of Electronics and Computer Science. There are only about 100, and 800 undergraduates and 420 postgraduates. So these are our campus. So my office is basically somewhere here at the top floor here. And yeah, thanks Professor Yusuf for introducing me. So I get my electronics degree and also PhD degree, all from University of Southampton. After my PhD, I did a postdoc for 3.5 years before I became a lecturer, and eventually I become associate professor. And since December last year, I was promoted to become a professor. And I was one of the founding member and officials of the IEEE Quantum Communications and Information Technology Emerging Technical Subcommittee. It's a long title. So basically what we are trying to do is that we're trying to popularize the research in quantum. And we do workshops and also conferences as well. So far, I have 15 PhD students graduated from me, and I've supervised more than 100 MSc project students. So yeah, published a lot of papers, 2 book chapters, and a few European projects, and also the British EPSRC projects. So let's go straight to the talk then. So the outline is as follows. I'm going to give you some background, followed by motivations, and then have a quick overview of the current developments, and then the overview of quantum physics. And then we go to the quantum search algorithms and the application of the algorithms. And then we talk about how do you protect the algorithms and also the hardware. And I'll give you the conclusion at the end. So a little bit background about quantum communications. According to Moore's law, the number of transistors on a microchip doubles every 2 years. The transistor size is expected to approach atomic scale, very small, in the near future, because as humans, we are so greedy. We want to make things to be so small and so powerful. So we have a few barriers to go over. However, when the things are so small, that's the first barrier. The laws of physics change. It is no longer governed by the classical physics. So the laws of the quantum physics become the laws of the small things. So in 2015, IBM demonstrated 7 nanometer node chips. 7 nanometer is so small already. And then now, in May 2021, you have 2 nanometer chip technology. So things so small now, 2 nanometer. And this is the predictions given by the International Technology Roadmap for the semiconductors. So according to the prediction, when these figures was produced in 2020, so it's about 10 nanometer. Yeah, but if you look at the IBM achievements, in 2015, you already have 7 nanometer. 7 nanometer is somewhere here. Yeah, so it's going up here. So, and now, 2021, you already have 2 nanometer. So 1, 2 is here. So we are basically slightly ahead of the game. And we are, however, although we are supposed to be in a quantum regime, but at the moment, the quantum computer is not so ready yet. So there are still a lot of things that people need to do to improve the system before it can be used as a computer. Yeah, for example, your mobile phone is more powerful than the computer in the past. Yeah, so to have the quantum chips on the mobile phone will take some years. Yeah, so it's not ready yet. Although the chip is so small now, 2 nanometer. So what are quantum technologies? According to the UK National Quantum Technologies Program, quantum technology can be viewed in 2 ways. The first one is in the first quarter of the 20th century, light and matter behave on a slightly difficult manner that classical physics cannot explain. So the quantum physics was used to understand the concept of the phenomenon. Yeah, for example, in semiconductor. So because of the quantum mechanics, people understand how electron and the whole works at energy level in the semiconductor. And then because of that understanding, we were able to have electronics that we have now. Yeah, the mobile phone that you have, the computer that you have. But when we talk about quantum technology, normally people mean the second part. The second part is basically we try to use the quantum mechanics. Instead of using it to explain things, we try to manipulate it. Yeah, we want to use the quantum effects to do something more powerful. For example, you want to have medical imaging devices. You want to have a quantum computer that can perform faster than the classical computers. And then if you can have quantum computer, then you can solve a lot of problems that the classical computer cannot solve. So that is the second part of the quantum technology that people are talking about. And why people talk about quantum communication? What is the motivations? Yeah, there are basically 2 or 3 things that is very attractive about quantum communication or quantum computing. First of all, the quantum entities allows people to do things in parallel. So if you can do things in parallel, then you can have a quantum computer that can do things in parallel without having to have 10,000 computers. You can do 10,000 things in parallel using just one quantum computer. So basically, it allows us to do parallel evaluation of a function at a complexity that is equivalent to a single classical evaluation. And because of that, quantum computer is capable of solving challenging optimization problems in a fraction of time compared to the conventional computer. Because the conventional computer, you either do it serially, one by one, or you have to buy so many computers to do things in parallel. But quantum computer, one computer can do things in parallel. So that's why you can have a fraction of time that's required, compared to the classical computer. And it can reduce the detection complexity. Because the quantum physics is different. If you can manipulate the quantum physics, then you can do things with a reduced complexity as well. The next thing good about quantum communication or quantum computing is that you can have secure transmission. You cannot copy a quantum bit. Classical bit you can just copy in a computer, but in the quantum communication, the bits in the quantum domain cannot be copied. Therefore, you can have a very secure transmission. So at the end of the day, we want to have a very fast and secure quantum communications. So these are some current developments. So in 2017, IBM built a 17-qubit quantum prototype. So 17 qubit is a bit like 17 classical bits are very small, isn't it, compared to what we have now. So this is 2017 17 qubit, and it was the most powerful quantum processor at that time. And then later on, they produced a 16 qubit processor. So IBM has been leading the game so far. And then in January 2019, IBM Q System 1, they have 20 qubits. And that is the first fully integrated universal quantum computing system. They even make it available on the internet. People can create an account. So for example, some of my students, we have account in this IBM Q system, and then we can run simulations. Right. And then before 2017, in 2016, China launched the world's first quantum satellite in August. So this is a quantum satellite. So they have some experiments. For example, in the Quest experiments, quantum experiment at space scale, Quest. Basically, they prepare 2 entangled photons. So the photon can be used to be like a quantum bits. So they have 2 entangled photons or 2 entangled quantum bits, and they beam down to 2 ground stations. So these 2 ground stations, they are more than 1,200 kilometers away. So they are doing very powerful, very interesting experiments. So the 2 qubits, they are linked to each other, although they are beaming down to 2 far away stations, but the quantum physics, the entanglement is still there. And based on this, the secure key can be transmitted based on the quantum key distribution techniques. So you can look into more detail from these 2 references. And then 1 year later, in September 2017, China launched a 2,000 kilometer quantum fiber link. So the quantum communication can be using light. It can also light in a free space. For example, free space, you beam the photon from the satellite to the ground. You can also send the photon through the optical fiber. So that was done in China as well. So connecting Beijing and Shanghai. So because of this, you can have unhackable communication. So basically, it's very secure. And the MESILS, the quantum communication satellite that we mentioned here is called MESILS. They also have some other things. For example, the world's first intercontinental quantum video call between Europe and China. And this satellite has also been linked or integrated with the quantum network on the ground. So this is the first space-to-ground integrated quantum network. So this is China. Again, similar to IBM, China is also doing a lot of interesting things in this domain. In 2019, Google's quantum processor called Sycamore processor, it used 54 superconducting qubits, and these 54 qubits can do a lot of interesting things that a classical computer needs to take years to perform. They can do it very quickly. So it shows that the quantum computing definitely can outperform the classical computer. In the past, everything was on theory, on paper. But now in 2019, they finally showed that. So this is basically the Sycamore processor, as you can see in the middle here. So this is the qubit basically located at the cross point. So that's 2019. And then in July 2021, just last month, China also have another quantum processor, and it's called the 朱中智 2D programmable quantum computers. 朱中智. And this surpassed Google. So this is even more powerful than Google's processor in 2019. This processor can support 66 qubits, and they use 56 of the qubits to complete a calculation in 1.2 hours. So this computation would take about more than 8 years for a classical computer to perform. So you can see how powerful it is. And at the bottom right corner, you can see that this is the quantum dots. Quantum dots. Basically, how the processor was configured. As you can see from here. Okay, so we have been talking about interesting thing, how the quantum communications or quantum computing can achieve. We talk about research, IBM, China. In fact, a lot of countries in Europe, in America, So throughout the world, there are many government spending a lot of money on the quantum projects. So let us now look at more details about quantum communications or quantum physics. As you can see from here, this is a bit like a globe, an Earth, on Earth. So a bit 0 is a bit like the North Pole. Bit of 1 is a bit like a South Pole. So that is a classical computing. Classical computing is basically either North Pole or South Pole. However, for a quantum bit is a superposition of 0 and 1. In other words, when you look at the quantum computer, the qubits could be any point on the surface. It could be here, it could be there, depending on the amplitude of the bits. And the amplitude square becomes the probability. So I'll go into a little bit detail later. So what you can see here, classical bit is basically 0 and 1 at the North Pole or the South Pole. A quantum bit is basically a qubit that can be located on any point on the surface. Okay, because this is a linear combination of bit 0 and bit 1. And this is called a Bloch sphere. It's not an Earth, it's a Bloch sphere. Right, so it looks like very difficult, very complicated. But actually, in terms of mathematics and theoretical study, a qubit is just a vector. Bit of 0 is 1 0, a column vector. qubit 1 is 0, 1. Okay, and then a superposition of these two qubits is basically like here. Yeah? So this is a qubit of 5 is alpha times 0 plus beta times 1. Okay, so this is basically how the superposition works in terms of mathematics. It's very simple actually, and writing them in matrix form is quite complicated. So that's why people use a direct bracket notation, as you can see from here. So instead of having the column matrix, you just do this one. Yeah, alpha 0 plus beta 1. And then when you have two qubits that's multiplied together, then you have a tensor product that looks like this. Okay, so to make life simple, people have done, let me move this away. Okay, so the tensor product between qubit A and qubit B can be simplified as cat AB, or that is, yeah, A and B in the brackets. A little bit about the quantum gate. So if you're interested to do quantum communication or quantum computing, first of all, don't be scared about the qubit. It can be represented by a vector. And the operation, basically there are only a few of them, and all of them can be represented by a matrix as well. So Pauli I gate is identity operator. The matrix is basically like this, identity matrix, 1, 0, 0, 1. Pauli X gate is basically 0, 1, 1, 0. Y gate is 0 minus I, 0. I is basically square root of minus 1. And Z gate is like this. Yeah, it's a phase flip. Yeah, it can change the phase of the qubit. Pauli X gate, if you multiply the qubit with the X gate, you have a bit flip. Yeah, 0 become 1, 1 become 0. Pauli Y gate, basically you have a bit and the phase flip at the same time. And then Hadamard gate is basically like this. Yeah, so although physically it's very hard to implement, but theoretically it is quite easy to do the simulation. So this is basically the matrix. Right, so a little bit more about the qubit. How can you have two things that is superimposed together? So as you can see from here, there are many ways to create a qubit. A quantum bit can be created in many ways. So one of the ways is basically to use a magnetic field. So for example, here, the blue one, yeah, is spinning downwards. The red one is spinning upwards. By changing the magnetic field, you can change the spin of the qubits. Yeah, as you can see from here. So to have the superposition of these two, basically you can have spin up and spin down, and at the end you have a superposition of that. Yeah. And the other way to look at that is that you have a coin. If you spin the coin, while the coin is spinning, you do not know when the coin stops, whether it will be head or the tail. So in other words, the amplitude is 1 over square root 2. Square of that amplitude give you 0.5. 0.5 means that the chances that the coin will stop at head. Yeah, when you stop the coin, you have a 50% of being head or 50% being a tail. Yeah. So a qubit is a bit like a spinning coin. The coin is still spinning and it's qubit. When you stop the coin, it's a bit like you do the measurements. If you do the measurements, then the qubit will collapse to classical bits. It becomes 1 and 0, or head or the tail. Yeah. And as I mentioned also, you cannot copy, you cannot clone a qubit. Yeah. And therefore you can have a secure transmissions. Right, so what do you mean by quantum parallelism? If you look at the top left corner, this is a serial computing. For example, among the 8 keys, one of the key is a solution to a problem. So to find the key, you have to try the key one by one. Yeah, so this is what the classical computer do. You try them one by one, serially. And at the bottom one is basically the parallel computing. So in order to do to make it faster, you can have 8 computers instead of 1. Yeah, each computer try one of the 8 keys. Okay, so this one is quick, time efficient, but resource is very inefficient. what happens if you need to find one solution out of a million? Then you have to buy 1 million computer. Yeah, that is very expensive. On the other hand, quantum computing, you can see from here, there's only one box. However, because of the quantum physics, you can try all the 8 keys at the same time using just one quantum computer. Yeah, if you want to try find the solution from 1 million keys, you just need to have enough qubits. Yeah, that's it. That's why just now when I show you that in July 2021, 56 qubits was used to solve a problem in 1.2 hours. Okay, so 56 qubit can allow you to do a lot of comparison, not only 8 keys, yeah, so many keys. So that's why it's very powerful. So for a B-bit, yeah, this is a B-bit classical register. You can only try 1 out of 2 power B combinations, one by one. But in the quantum computer, you can try all of them. Whenever you apply a gate, X gate or Y gate or Z gate, the gate will affect all of the states. Yeah, 2 power B states. Right. Okay, so this is basically I've told you about the development and the overview of the quantum system. Now let us look at the application. Yeah, and let's look at quantum search algorithms. So this is one of the example, and this was invented by Grover, and this system is called the quantum search algorithm. Yeah, so this is Grover's quantum search algorithms. So what you see here is that you want to find one answer from a list of n elements. So in this case, we make the simple system to be very simple. You have only 4 elements, and you want to find the answer. Okay, so as I told you earlier, a quantum system, a qubit, for example, is in a spinning state. Yeah, it's not 0 or 1. It only becomes 0 or 1 when you do the measurements. Okay, how do you do the searching without doing the measurements? So this is what you do. So first of all, you prepare the qubit or the state in equiprobable starts. So 0.5 is the amplitude. Square of that is 25.25. Yeah? So 25% of them. If you do the measurement, you will find that the answer is here 25%. Answer here 25%, 25. Yeah? All of them sum up to 100%. So initially, you initialize everything to be equiprobable. And then there is a system called the oracle. The oracle operator in the computer, it can find out the answer, and then you use a phase inversion. Okay, so this oracle, although it knows the answer, but you do not know it until you do the measurements. But this oracle can be used to modify the states. So everything here is done internally. We do not know the answer because we have not done the measurements. So the oracle operator find out basically this is the answer. Then you can phase inversion it. Do the phase inversions, and then you find out the mean value. So 0.5 times 3 plus minus 0.5. The mean value is somewhere here. Somewhere here, this line. And then after the phase inversion, the next step is the inversion about the mean value. So from here, 0.5, you flip around 0.25, you go to about 0. This one, go to 0. This one, go to 0. Okay. And then this one, at the bottom here, when you flip over, it go to the top. Almost equal to 1. This one, go to 0. So basically, that is called one iteration. B and C is basically one iteration. So after one iteration, you can find the answer. Among the 4 elements. In real life, there will be maybe millions of elements rather than 4. Okay. So how many iterations is needed is basically based on this equation: pi over 4 times square root of how many elements divided by how many solutions. So in this case, there are 4 elements, 1 solution. Square root of 4 over 1. Multiply by that, and then you find out the value. This is about 1 point something. So floor operation means 1. So that's why you have 1 iteration is sufficient. However, if you do it again, one more iteration. After you have found the answer, but somehow you forgot to stop the iteration, you go further, something weird happen. If you go to do the inversion and inversion about the mean, the second iteration will give you the one in the green. Yeah. So although it's positive and negative, but the probability is basically the square of that. Yeah. So basically 25% here, 25%. So at the end, this is similar to in the past. So in this quantum search algorithm, you need only one iteration. If you go further, the answer will be wrong. Okay. So this is basically a very interesting 2D map. The number of global iterations versus the number of qubits. So if you have 2 qubits, 2 power 2 equal to 4. Yeah. So this one is basically 2 qubits. 2 qubits. Yeah. So you can see that the red one here, one iteration. If you go to 2, it becomes blue, 3, and 4. So 1 iteration and 4 iteration will give you the answer. So you can see that it's a little bit periodic. If you have 8 qubits, yeah, 2 power 8 is a lot, then you can see that at this iteration, yeah, about 13 iteration is needed. Yeah, so you can see that there is some kind of periodical nature in this quantum search algorithm. And throughout the years, since the invention of this global quantum search algorithm in 1996, there have been many people inventing a lot of things, yeah, to improve the system. Okay, so let me go forward a bit. So Shor's algorithm. So this is the configurations, yeah, for the algorithm. So you can see here at the top is a control qubit. At the bottom is a qubit that is being controlled. So QCR is a quantum control register, which consists of C number of qubits. And then QFR is the quantum function register. Yeah, so this is a function. So if this is a 1, then this function will be active. If you're 0, you will be inactivated. Yeah, so basically that's why we call it control. And here the one in the yellow is the inverse quantum Fourier transform. And then here is observation. So observation is a bit like measurements. So when you do the measurements, then the qubits will collapse to classical bits. And this Shor's algorithm was invented in 1994. It's used for factorizing an integer number. Yeah, so this is basically one of the applications. And then people develop it further into quantum phase estimation algorithm. So if you look at them, the only thing different is that in Shor's algorithm, the qubits are all initialized to 1. But in the phase estimation, it's a qubit. So this is a superposition of 1 and 0. Okay, so this is the only difference there. And the rest of them are very similar. So this was invented in 1998. It's used to estimate the eigenvalues of a unitary operator. So this is very technical terms. Yeah. So Shor's algorithm is a specific application of the phase estimation algorithm here. And then the quantum counting algorithm is further developed based on the phase estimation. So the difference now is that you initialize them to 0, and then you use the Hadamat gate here. Okay, and then G here is basically the global operator. Yeah, so you can see you still have the control bit, and this is the control will determine whether this function will be activated or not. And then you go to the quantum mean algorithms. So this one is a bit more complicated now. So after the observation, you can do these computations. And also here, yeah, you have this air prime operation. So these are very technical, very detailed in technical terms. What I'm showing you is that quantum mechanics has been used to develop into quantum algorithms, and all these algorithms step by step that leads to something that is useful, and finally you can use it for to solve the problem that we are facing. Right. Then after the quantum mean algorithm, you can further develop it further into the quantum weighted sum algorithm. So the difference between that is that this is a hadamat gate. You change it into a rotation gate here. Yeah. So, and then you go further. Yeah. So after that, this can be used for solving quite a lot of information, a lot of things now. For example, you can have a quantum multi-user detector. So if you are working in the communications, basically there are many users connecting to the base stations. If all the users are transmitting at the same time, then you need to find out a way to detect all the users. So this is basically the quantum assisted multi-user detector that can use these algorithms. So this is what I mean by that. Each user has one antenna transmitting the signal. User 1, user 2, user 3, you can have many users. If you have 20 users, each of them transmitting 4 points, yeah, so this is a constellation, 4 QAM. Then how many combinations that the base station need to detect? The answer is 4 points to the power of 20 users. Just 1.1 times 10 to the 12 is a lot. Yeah, it's a lot. So if you want to detect them all at the same time, then you need a very powerful computer. In the mobile phone that you have, if your mobile phone is a 3G, they do not do this. They use a CDMA. Yeah. So basically, they do the spreading. They multiply them into different chips, and then they can minimize the detection complexity at the cost of using more bandwidth. So here is that if you do not want to use more bandwidth and you want to detect all the 20 users together, then the computer needs to be very powerful. If you go to the 5th generation of wireless communication, 5G, there are many promises. So one of them is a massive machine type communication. So you are talking about 20 users. How about 2,000 machines want to talk to each other? Yeah, massive machine type communications. And also you want to have a low latency, ultra reliable, very good performance, yeah, low errors, very reliable, and very low delay. Yeah, so this is a very difficult challenges, yeah, that people need to do. And at the same time, they also promise 100 times higher throughput. Yeah, for example, in the enhanced mobile broadband communications. So in other words, 5G is there now. Yeah, although they are using tricks like multiple antenna or multiple more bandwidth, but the complexity of future generation wireless communication is going to be increased to a point until the classical computing will not be sufficient. Yeah, especially also now that the semiconductor, yeah, 2 nanometer is so small now. So this is a quantum multi-user detector that I mentioned earlier. You have the quantum search algorithm proposed by Grover. It's a very specific part of a bigger circle. This bigger circle was algorithm proposed by Boyer, Brassard, Hoyer, and Tapp. So these are the author. Yeah, they call this algorithm BBHT algorithms. So Grover's algorithms, you need to know how many solutions you want to find. You want to know what kind of solution you want to find. And the bigger circle, you do not know how many solutions. Maybe there are 3 solutions, but you know what you want to find. And the bigger one, do Hoyer algorithms, you do not know how many solutions. You do not know what kind of answer you are looking for, but you know something. Yeah, you want to find the minimum of a function. Yeah, so this can be used for the multi-user detector. So if you want to look into more detail, you can download this paper. Yeah, this is basically published by my student. Yeah, co-supervised by myself and Professor Hanzo. It was published in 2013. And quantum multi-user detector has been developed quite a lot. So these are all our paper. Basically, we published in 2013, 2014, and also 2015. And even now, yeah, we still got a lot of publication. But if you are interested in multi-user detector using a quantum computer, these are basically a very good starting point for you. The next application is joint channel estimation and the multi-user detector. So on one hand, the signal that you receive, you have the pilot. The pilot can be used to predict the channel state information. And the signal that you receive also have the data that you transmit. So that can be used for the detecting the data from the different users. So both of them can have iteration. You can see the arrow here. You can have iterations. Yeah. So here you got a quantum channel estimator. You have quantum multi-user detector. Yeah. So that can be used to detect them. So we published a paper on this as well in 2016. So if you're interested, feel free to download and have a look. Right. So multi-user transmission. So just now we talked about multi-user detection, but this is multi-user transmission. Yeah, different user transmit by doing some tricks onto the signal that you transmit. Before you transmit, you multiply with some kind of beamforming matrix. And how do you find out the matrix? Basically, you can use the quantum computing to find out the matrix. Yeah, so that we propose a quantum-assisted particle swarm optimization (QPSO) algorithms, and it was published in 2016 as well. So multi-objective routing. So this is a routing where you have multiple objectives. For example, you want to minimize the bit error rate, you want to minimize the power consumption, you want to minimize the delay, and at the same time, you want to maximize the achievable rate. So there are already 4 objectives. So from the source node transmitting to the base stations, there are 5 possible mobile devices that you can use. Here, you can go up to here. Here, you can go straight. You can go here, there. Yeah. So there are many possible ways. If you have many mobile devices in between, then the number of routes will be even more. Yeah. So let me see if I can show a demo here. Yeah. So you can see here, at the moment, the yellow one, and now the blue one. So let me stop somewhere over here. Okay. So basically here, there are two possible ways. Both of them are optimum. Yeah. Optimum in the sense of minimizing the BER, bit error rate, and also the power. So here you can go straight this line, the blue one, yeah, using R3, R1 to destination, or you can use the orange one, R3, R2, R1, and destination. So both of them. So this is called the parallel optimal. Parallel optimal in the sense that there are multiple objectives, and the solution is not one. Yeah, the solution is multiple solution on the parallel front. And for more detail, yeah, feel free to look at this paper. Right, let me move on. And the 5th application is the multiple objective routing and load balancing. So you can see here, you have client, the mesh client, the human are the client. So 1, 2, 3, and 4 clients. And you also have the mesh router. Yeah, the router, yeah, looks like the antenna here. So on the left-hand side, you see is a topological of the 4 client and 4 routers. And on the right-hand side is basically the representation of the 2 layers. You can divide them into 2 layers. The human, yeah, the online social network layer. And the next one, yeah, is the wireless mesh network layer. So what happens is that the human layer, they might know each other. Yeah, for example, on the Facebook, yeah, the friendship status. So client 1 know client 3 and 4. Yeah, so you can do these things in 2 layers. And because you got so many layers, the complexity will increase very quickly. So that's why you need a quantum computer as well if you want to find out the optimum solutions. So this was one of our other applications that we published in 2016. Next one is the indoor localizations. So in figure A, you can have user here, you can have millimeter wave anchor here. Okay, and B is A is uplink, B is a downlink. Yeah, you can use the LED access point. So you can combine visible light communication with the quantum communications. So what you see here is that some people have been working on the visible light communication. So some of our researchers in the group here in Southampton are also doing that. So basically, for example, the light, for example, you go to somewhere, yeah. For example, you from Malaysia, you want to fly over to Southampton, and on the flight you got the reading light. The reading light can shine onto your book. So what people are trying to do is that you can use the light not just for reading books, but also use the light to communicate. as long as you have a mobile phone or some devices that can detect the light, you can encode the information on the light so that your devices can get the information. Yeah, so you can use the light for the communications. So this paper was called Quantum Assisted Indoor Localization for Uplink Millimeter Wave and Downlink Visible Light Communication System. So it was published in 2017. Yeah, so you can see, yeah, localization means that you want to find out where is the location of the user. Yeah, and then you can also have more communication and to serve the user by using this downlink. Right, so we have been talking about a lot about the wonderful thing that quantum communication or quantum computing can offer. However, there is a flip side. Basically, the quantum bit or qubit is very fragile. If you got noise, then the noise will corrupt your qubits. And the quantum gate that you have, yeah, when we talk about the oracle, the Halamat gate, the phase inversion gate, all of these gates are also prone to noise. Yeah, so if you have noise, for example, at location P1 before the oracle, P2 after the oracle, and P3 after the Halamat gate, P4 after the inversion gate. So each of the location of the error can have three types of error. It can have bit flip, it can have phase flip, it also can have bit and phase flip at the same time. Yeah, so it's a bit complicated. If you look at this diagram, yeah, so I have shown you before. So by using Grover's algorithms, you can find out the solution. So for example, this line is the location, or basically the number of iterations that is needed to find the answer. And the one in red, dark red means that very close to 100%. The one in blue means that very close to 0%. Okay, so what happens if you got errors? Yeah, so here is you have error just before the oracle. Yeah, so A is you have one error for every 10,000 bits. Looks still okay. If you have one error for every 1,000 bits in B, you can see that the blue color is actually more now. The red here, you see, there's no red here anymore. Yeah, if you have 13 qubits, then it's very hard to find the answer anymore. If you have 5 error in every 1,000 qubits, then you can see that, yeah, it's a bit like the blue sea is coming over. Yeah, the land disappear now. So you can see, yeah, it's very hard to get a solution. If you have one error for every 100 qubit, then basically it's a bit like tsunamis now. The sea comes over. Yeah, your quantum device cannot work anymore. Yeah, so for that reason, you need to find a way to remove the error. Some kind of error corrections. Okay, so this is one of the proposed systems that we have in our group. So it's 2016 that we have our paper. It was published in Nature Scientific Reports. So what you see here is that without the quantum error corrections, yeah, the success probability is quite low. When you have error codes, for example, Steen's code, then the success probability will increase significantly. So that was basically, we show that error correction is very important, not just for classical computer, but also for the quantum computer. And further contribution in the quantum error control codings can be found, for example, in this list. For more paper, you can go to my publications. So, for example, in 2020, we published a paper on the gate error resilient quantum Steen codes. So we try to improve the quantum error correction codes, yeah, by doing some tricks onto the gate. And here is a quantum topological error correction code, yeah, that can be used to improve the performance of the Clifford gate. So that was in 2019. So these are all the publications in our research group. Okay, so the conclusion is that the quantum search algorithms or quantum detection algorithms are capable of offering fast and efficient detection for a wide range of communication scenarios. The future generation wireless communication system require quantum error detection because of the high complexity to support the high requirements. The practical implementation, on the other hand, require us to look at the effect of the quantum noise, and therefore quantum error correction schemes are very important, and this is the natural remedies to protect the quantum algorithms. So thank you for your attention. This is our research group. So the photo was taken about 4 years ago. So you can see that our group is very international. The head of the group is Professor Lau Sanzo, the one in the red. And we also have a few people here. Yeah, so I was here as well. Right, so thank you very much. If you have any question, feel free to ask me. Thank you.
Thank you, Prof. Michael. There are a few questions from one of the audience in Facebook, but I think you have addressed most of the questions. Like, for example, what are the capabilities of quantum-assisted communication? I believe you have talked about that. What are the current technical challenges? You already covered on that one as well, and the application scenarios. You have shown us some example of the application scenarios. But perhaps there's one question that I will show you here. What are the applicable transmission protocol for quantum-assisted communication? And what are the advantages and disadvantages of these protocols? Is there a dedicated transport protocol for quantum-assisted communication? Perhaps you can help to answer this question.
Okay, so right. So basically what we are doing here is not everything quantum. So basically we integrate quantum and classical. So your mobile phone will have, what we propose that your mobile phone has a quantum chip, but everything else, the base station, everything, they transmit normally. But then when you receive the signal, you receive classical signals. You want to find a solution to a classical problem. But to find the solution, you need to use quantum algorithms. That's where you have the quantum chips. Yeah, the quantum chip will use multiple qubits to do things in parallel, 2 power b, for example. Yeah, b is number of qubits. The more qubits you can support, then the more parallelism you can do. So there's no need for a transmission protocol in that sense, because everything is classical. Yeah, so that is a detection part. Yeah, the detection could be your mobile phone. The detection can be at the base stations. So advantages are basically you can do things very quick. Disadvantages is basically the hardware needs to be ready. Yeah, at the moment we only have 66 qubits, and although you can solve a problem that require 1.2 hours, which need to be solved by a classical computer that take 8 years, but that is still not enough. Yeah, so basically we need to develop it further. So this is the disadvantage. Disadvantage is that the quantum computer is not ready yet. So the last part of the question, dedicated transport protocol, there's no need for that. But there are many things that you can do. For example, the quantum key distributions. So for QKD, quantum key distribution, then you need to have some dedicated transport. So basically you need to have, for example, the photons, yeah, transmitted from the satellite to the ground. Then you have a continuous variable, discrete variables. So it's a bit complicated, yeah. But if you are talking about quantum assisted detections, then it's easier. Yeah, everything is like a quantum computer. Yeah, you can have a quantum chip at the base station, and then everything else are classical. So in that case, there's no need for the dedicated transport protocol. I hope that I answer your 3 questions here. Thank you.
Okay, thank you. I think we have time for one more question. Perhaps I can again. There is one question from Ruzi Ziauddin. Is the quantum communication about search algorithm based on qubit? Can it be applied on resource management? Can you tell about the complexity compared with other search algorithm like GA or PSO? Yeah. On Ruzi.
Right. So the algorithm that I'll show you, I think I showed you quite a few already. Yeah, for example, quantum Grover search and means, the phase rotation, all these things. So you look at the circuit, at the beginning, you need to have qubits. You need to prepare the qubits. The qubit could be initialized to 0, could be initialized to 1, it could be initialized to be equiprobable. So in that sense, you need to have a qubit. So without the qubit, you cannot do anything. So the power of quantum computing is because of the quantum mechanics that is inside of the qubit. And the qubit is some kind of particle that's very small, 1 nanometer, for example, very small. And because it's so small, you have to use the quantum physics to explain it and to manipulate it. So therefore, you need the qubit. And then it can be applied to many things, not only multiple user detection and other things. You can also for resource management. You got limited time slot, limited bandwidth, limited number of antennas, limited number of limited transmit power, for example. So all these are all the different objective, different constraints that you need to optimize. So that can be applied to any optimization problem. So the complexity, if you have a quantum computer, so as I mentioned earlier, you can have parallel computations with a complexity of 1 evaluation in a classical computer. The question that we have here is that the classical computer is so small, the mobile phone is so small. And then the quantum computer at the moment, if you look at the IBM machine, it's so big. So the complexity depends on the hardware of the quantum computer at the moment. At the moment, the quantum computer is very expensive, it's very bulky, very big. You need to prepare them in a very low temperature, for example. So once the quantum computer is very small, compared have the same scale as a classical computer, then the complexity reduction will be significant. Hardware and other things. But as you can see here just now, the team by Google and also by China, they managed to do optimization. For example, the 1.2 hour optimization that take 8 years for the classical computer to do. But that 1.2 hour computation, the computing power, the machine is very big. Compared, you need to. What I'm saying is that although the time is very short, but then the hardware is not as small as a mobile phone. And then if you want to compare to genetic algorithm, particle swarm optimization, at the moment, you can combine them together. So we are people working on machine learning and quantum communications. So instead of comparing them, fighting them, let them competing against each other, you can use them together. So machine learning can be used to support quantum communication. Quantum computing can be also used for to support the machine learning. If you want to look into more details, then when the quantum computer is ready, then it can outperform the machine learning as well. So that is the short answer I can give. Thank you.
Okay, thank you. I hope that answers your question, Lucy. I think that's about the time that we have, Prof. Michael. Thank you so much for the very insightful information on quantum communication, quantum error communication. I think it was very helpful and quite informative. We have seen how your research group has worked towards that, and hopefully we can collaborate in future works on this quantum error communication. And once again, on behalf of IEEE Communication Society and Vehicular Technology Society Joint Chapter Malaysia, we'd like to thank you so much for spending your time and with us this afternoon. Thank you.
Okay, thank you.
All right, thanks. Bye.
Okay. Bye now. Bye.
Thanks, everybody.
Using Powtoon.